I am Ola Oitoba and I'm presenting a paper titled Empirical Measurement of the Water Vapor Resistivity Property of Typical Australian Membrane. The aim of this research is to establish the most appropriate methodology to quantify in the laboratory the water vapor resistivity properties of construction material in Australia. And at this time, I will be discussing the following: the background to this study, the literature review, methodology, discussion, conclusion, and recommendation. The condensation aspect of the new Australian Building Regulatory Framework expects that new buildings should demonstrate the capability to passively manage water vapor diffusion, and also that the individual elements to become wet and dry without causing moisture accumulation or mold growth in the building envelope. Internationally, agrothermal modeling has been identified as key scientific and administrative approach to manage condensation and mold in new buildings. In this slide, we have a short movie. The upper part of the movie indicates the temperature flux across a timber frame wall, while the downward part indicates the moisture flux across the same timber frame wall. The essence of agrothermal modeling is to predict the point of possible moisture accumulation over a period of time in order to prevent mold growth. The technical implication of Australian regulatory framework. To demonstrate NCC compliance, the verification method requires the completion of a agrothermal simulation. Agrothermal properties of individual material that makes up the building envelope are also required. Agrothermal loads on envelope are also required to be determined. The water vapor resistivity properties of construction material are required to be established. At this point, there are no data for the water vapor resistivity property. And how do we source for real and validated construction material agrothermal input data? This can only be done in the laboratory. This slide describes the methodology for this research, and it involves selection of pliable membrane common in Australian residential construction, testing the material sample in both dry and wet cup under varying climatic conditions, calculating the water vapor diffusion property from gravimetric method. It is important for me to mention at this point that Australia Construction Code expects that this experiment be carried out under 23 degrees Celsius and 50% relative humidity. Internationally, this has been critiqued as inadequate because of the variable nature of some construction material and also because of the variable condition that exists in new building. And due to the limitation of this current international test method, the method adopted in this research included varying the relative humidity and the temperature within the test room. This variable environment was established to determine if varying agrothermal loads has any influence on the water vapor resistivity property of the tested pliable membrane. Note that this paper reports on the test completed on 23 degrees Celsius and 35% relative humidity, and 23 degrees Celsius and 50% relative humidity. This slide shows the gravimetric measurement procedure. And gravimetric measurement involves determination of change in mass of water vapor that escape or enter a material under test. This method can either be wet cup as indicated in the slide or dry cup test. Like I said, after the gravimetric measurement, it is important to estimate the mean temperature and the relative humidity for the period of gravimetric measurement, which is now used for the calculation. The graph on the left hand indicates the observation during test 1 with average temperature of 22.5. The graph on the right hand shows the relative humidity with an average of 36%. For the second experiment, the graph on the left of this slide indicates the observation of the temperature with an average at 22.9 degrees Celsius, and the graph on the right indicates relative humidity with an average of 50.4. This slide is showing the result of the calculation obtained for the water vapor properties of specimen A, and it is important for me to point out all the properties that make up the water vapor resistivity. Number 1, we have the water vapor flux here. It's a very important property. The water vapor permeance, also very important. The water vapor resistance, very important. We also have the water vapor permeability, the water vapor resistance factor, mu value, and the water vapor diffusion equivalent air layer thickness. All these values makes up the water vapor resistivity properties. However, it is important to point out that the water vapor resistance factor and diffusion equivalent air layer thickness are required for ergothermal simulation. This slide shows the result of the calculation for the water vapor property of specimen B at 35% relative humidity. This slide also shows the calculation for the water vapor properties of specimen A at 50% relative humidity. This table in this slide shows the result of the calculation of the water vapor property of specimen B at 50% relative humidity. This graph indicates the dynamic behavior of this pliable membrane, as this membrane diffused water vapor resistance in different manner for the wet cup as opposed to the dry cup test. And for the diffusion air layer thickness, the trend is also similar. The summary of this result, as shown in the table below, indicate that each pliable membrane has different vapor resistance property when placed in different environmental conditions. While this preliminary result indicate that pliable membrane behave differently when exposed to different relative humidity conditions, this is contrary to the static modeling and measuring method referred to in AS 4200. As only 2 tests being conducted, the future tests at greater relative humidity values will provide further evidence of a linear or non-linear relationship. In conclusion, this paper reports the test completed to ascertain if the water vapor diffusion property varies with relative humidity or not. This preliminary result indicates that water vapor resistivity property of sample tested were different for 35% relative humidity and 50% relative humidity. These initial findings demonstrate that the current methods as described in ISO 12572 and AS 4200 may be inappropriate. As only 2 tests being completed, the next stage of research will see the test room being kept at 23 degrees Celsius, but the relative humidity will be changed to 65%, followed by 85% relative humidity. Thank you.